Hello everyone. My name is Anudh Mishra and I am a MBBS student at AIIMS Bhuvneshwar. Today I'm going to discuss the second part of the chapter surface chemistry. Excuse me. Second part of the chapter surface chemistry with you all. So today we are going to cover colloids. Right. What are colloids? According to classical definitions, colloids lie somewhere between your true solution and suspensions. Pardon me. Yeah, so as we were discussing, what are colloids? Colloids are something which come between the true solutions and suspension. So in a true solution, all the particles are uniformly dissolved in the solvent. Whereas in a suspension, they are just suspended or they are not uniformly present throughout the solution. If you scoop out a portion of true solution, you will find uniform concentration of solute in the solvent. But in suspension, if you scoop out any random portion, you will find different concentration of solute in the solvent at different places. Suspension and true solution are the extremes of mixtures. All right. So, what are colloids then? So, they are a bit complicated. We cannot say that they have some properties of suspension, they have some properties of true solution, although they have, but we have to define them giving an original definition. Okay. How do we define colloid classically? Heterogeneous system in which one substance is dispersed as very fine particles in another substance called the dispersion medium. There is a dispersed phase in a dispersion medium. Usually, dispersion medium is more or in quantity, it serves as a solvent basically. And the dispersed phase has a characteristic that it is present as very fine particles. So, it is not molecular. What do you understand by that? Suppose there is a chemical XX. This is a chemical. Okay. I designate this chemical as chemical X. Okay. Now let me create a beaker. What will happen in a true solution is chemical X will be present uniformly. Just a second. It will be present uniformly throughout the solution. But in case of a colloid, suppose I take a beaker like this, it will be present in aggregates. Although they are fine, very fine, but they are not in molecular terms. So X aggregates of X will be present. Okay. Usually it is seen that the composition of any place is uniform. So yeah, you're getting some part of this and a whole. Here also you're getting a whole and some part of this. So composition might remain. Usually it remains even throughout, but there are exceptions. All the three subjects, especially chemistry. Direct questions are being asked nowadays from NCRT. You'll miss those questions. You'll be confused in those questions if you don't, read NCRT at a regular interval. NCRT says colloids are classified based on physical state of dispersed phase and dispersion medium, whether they're solid, liquid, or gas. Then nature of interaction between them and the particles in the dispersed phase. So whether they are ions, they are molecules, and various other kinds of particles. Okay. Then the first classification, physical state. We have a solid dispersed. Okay, let us generalize a few things. Let us say a solid dispersed phase is dispersed in a medium of, we'll just divide this into some parts. So there is no gas dispersed phase which is dispersed in a gas dispersion medium. Gas always form true solutions. Okay. So yeah, we have our first category where the dispersed phase is solid. So if dispersion medium is also solid, it is called solid sol. If dispersion medium is liquid, it is called sol. Again, if dispersion medium is gas, it is called aerosol. Need to remember all the examples. Okay. Colored glasses, gemstones are solid sols, paints and cell fluids are sols, and aerosol is smoke and dust, where solid is dispersed in gas. Next, liquid dispersed in solid is gel. You can easily identify the characteristic of a gel. Dispersion medium is solid, but liquid is dispersed in that. What does that mean? It essentially means that, have you ever seen a gel? In a gel, it is kind of semi-solid. Okay, it is kind of semi-solid. So you can call it gel. Example is cheese, butter, and jellies. Liquid dispersed in liquid. Example is it is called emulsion, and example is milk and hair cream. Milk is a great example of emulsion because there is a hydrophilic dispersion medium and dispersed phase is hydrophobic. So the oil particles or the fat particles, fat globules in the milk are dispersed in the homogeneous dispersion medium, which is the aqueous compartment. Then liquid dispersed in gas is aerosol again. So some repetitions, yeah, we are finding some repetitions. For example, aerosol, then solid sol. So just remember, dispersion medium is if the dispersion medium is solid, it is always called solid sol. If the dispersion medium is gas, it is always called an aerosol. Then gas dispersed in solid, again solid sol, but this time the example is pumice stone, foam, rubber. So in question in exam, they might try to confuse you using the term solid sol. They might not give glasses, gemstones, they might give you foam rubber. Foam rubber, hair cream, butter, and cloud. They'll ask which of them is an example of solid sol. Go with foam rubber. Don't always remember that solid and solid is solid sol. Even gas and solid is solid sol. Only exception is a liquid and solid, which is a gel. Moving on, gas dispersed in liquid is called foam. Essentially, you have seen foam, right? You can easily understand why it is called foam because it is light as gas, but it still has liquid in it. Okay, so if you can contain it in a container, it'll take the shape of the container. It feels kind of liquidy, but there are gas bubbles in it. It is light. Okay, that is why it is called foam. Example is whipped cream, soap lather, and froth. Done. We are done with the first classification. So remember, NCRT emphasizes on sols, gels, and emulsions. These three are the most widely recognized colloidal systems that we come across in daily life. So sols are solids dispersed in liquids, gels, liquids dispersed in solids, emulsions, liquids dispersed in liquids. Okay, so sols, gels, and emulsions. Remember, we're going to take up discussion of sols and emulsions further, but you should remember the previous classification thoroughly. Okay. Then if the dispersion medium is water, the sol is called aquasol or hydrosol. If the dispersion medium is alcohol, it is called alkosol, and so on. Just an additional information which they also might confuse you saying which of the following is an example of aquasol. So you have to choose where the dispersion medium is aqua or water. Right. Then the next classification is based on nature of interaction between the two phases. Suppose the phases are happy with each other. We'll take it as this. Suppose the two phases are happy with each other. They want each other's company. So they are kind of what? They have affinity towards each other. They are called lyophilic souls, solvent attracting. And suppose the two phases, they hate each other. They don't even want to see each other. They are kind of enemies, which means solvent hating, solvent repelling, and they are called lyophobic souls. Both of them have different characteristics, which we will discuss later. Okay. So discussing lyophilic souls first. Lyophilic colloids. The lyophilic term means liquid loving. Huh? And examples are gum, gelatin, starch, rubber. Okay. Mixed in a liquid, right? An important characteristics is that if the dispersion medium is separated from the dispersed phase by any method, Sol can be reconstituted by simply remixing the dispersion medium. That is why they are reversible sols. So even if you separate the two components, this is the colloid, you separate the two component, again you can remix them and shake to get back the colloid. Definitely the dispersed phase will be like kind of semi-solid. Dispersion medium is usually liquid. So the semi-solid thing, if you add again in the liquid and mix it, it will become a sol. Why? Let's go a bit deeper. What happens is, see what is happening in a lyophilic colloid is the suppose these are the solvent molecules. The solvent molecules is surrounding the dis or the dispersion medium is surrounding the dispersed phase like this. But this is for any colloid, okay. But suppose the dispersed phase exists like this. Now you have to do something in order to break up this semi-solid material into these small particles, aggregates, so that they can move about freely in the solution. So what you'll do, you'll add dispersion medium and shake. So on shaking, a little pieces, a little quantity of them will be taken up. The dispersion medium will take up a little bit of quantity because there is attraction between the two phases. So it will bring some of them, the ones on the surface will start kind of dissolving because the liquid is attracting them and they will become colloids again. That is why they're called reversible sol. Next is lyophobic sols, liquid hating. Okay. Substances like metal and their sulfides, when simply mixed with the dispersion medium, do not form the colloidal sol. Okay. They are prepared by special methods. You cannot just mix them like lyophilic sols. Okay. And also they are readily precipitated on addition of small amounts of electrolytes or heating or shaking. So they are not stable, irreversible stones. Okay. They need stabilizing agent for preservation. So it is kind of we are forcing these two phases to remain in a colloidal state. They don't really want to be in the colloidal state. They'll try all possible ways. They'll make all possible excuses, kind of like you'll add any electrolyte, they'll want to disrupt. If you heat them, they'll want to disrupt. You shake them, they'll want to disrupt. But to keep them together, we need a kind of enforcer or policeman, which is called stabilizing agent, so that these souls are stable. Okay, so this is about lyophilic and lyophobic. Then there is the third classification. This is not a regular classification like the previous ones. It is kind of, you have to remember some things into this. First one is like, this is based on type of particles in the dispersed phase. Okay. First one is known as multimolecular colloids. So here the dispersed phase is composed of large number of atoms, or either atoms or molecules of a substance aggregate together to form species having size in the colloidal range. Only this much you need to remember. Okay. For example, sulfur soap. So yeah, small molecules are there, small atoms are there, but they aggregate together to form a colloidal particle. So they are called multi-molecular souls, because more than one molecules are involved. Then macromolecular colloids. Here, macromolecules. What are the macromolecules? You learned in biomolecules that proteins, fats, carbs. These are the macromolecules in the scientific term. If this macromolecule, they are in the size of colloidal range, they will form colloids. Okay, they are quite stable, resemble true solutions in many aspects. So this is an important point which is usually asked in exam. They resemble true solutions in many aspects. Then examples are starch, cellulose, proteins, nylon, polystyrene, synthetic rubber, and all. All of these are macromolecular salts. The next example is associated colloids or micelles. You have heard of the term micelles previously, right? You have heard of the term micelles previously in soaps and all. Okay, how do soaps work and all? We'll see that. But associated colloids are, see, they at low concentration they are electrolytes, which means they form a true solution. But at higher concentration they exhibit colloidal behavior. Okay, what happens is, suppose this is the beaker. At low concentration they will be true solution, kind of a true solution. But when concentration increases, they will start forming aggregates of the colloidal size. Okay, and they will behave as colloid. This is what happens. And these aggregates are called micelles. Okay, formation of micelle takes place only above a particular temperature called Kraft temperature, and only above a particular concentration called critical micelle concentration. On dilution, these revert back to the individual ions. Okay, then examples are soap and detergents. CMC of soap is given. These colloids have both lyophilic and lyophobic parts. So what happens? We'll see that in structure of micelle. So mechanism of micelle formation. This is a molecule of sodium stearate. We have kind of an ionic part here. Let us designate this as head, and this is lyophilic. Whereas this hydrocarbon part, which is hydrophobic, it is also lyophobic. Lyophilic, lyophobic. See, this is hydrophilic head and hydrophobic tail. Hydrophilic head is lyophilic, hydrophobic tail is lyophilic. So how do they aggregate? So this is at low concentration. They exist as ions, but at high concentration, they become aggregated like this. They form a kind of aggregate in which your lyophilic parts are outside facing the solution, like the dispersed medium, and lyophobic parts protect themselves from the solution by going on the inside of the aggregation. Okay, and this is called an ionic micelle. Surface of a sphere. Okay, C double bond O, or the lyophilic part. Examples: detergent, sodium lauryl sulfate. Polar group is SO4. Okay, then cleansing action of soap, nothing. There is this, suppose that this is grease. Grease is hydrophobic. So all the hydrophobic tails will get embedded in grease, and they will remove the grease, bring it on solution, which you can wash off. Okay. So yeah, here soap molecules form micelle around the oil droplet. Okay. Since the polar groups can interact with water, the oil droplet is surrounded by stereotypes, is now pulled in water and removed from the dirty surface. Soap helps in emulsification and washing away of oils and fat. Negatively charged sheath around globules prevent them from coming together, forming aggregate. So yeah, they don't form aggregates. They remain in the solution and they can be washed off. Right. So remember we were discussing about lyophilic and lyophobic colloids. So all the classifications is done. Now we'll go to preparation of colloids. See, lyophilic colloids can easily be made by shaking the two phases together. Lyophobic is the difficult one. So we'll just learn methods how to prepare a lyophobic colloid. So there are chemical methods, electrical methods, there is peptidization. Okay, these four methods. We'll see purification, ultrafiltration, and finally we'll see the properties of colloidal solution and some examples and this applications. Going to the chemical methods, the examples which you need to remember is all these examples, which is going as double decomposition, which is oxidating, which is the reducing reaction, which is going hydrolysis. Okay, double decomposition, oxidation, hydrolysis, reduction, all four and example. Remember directly. All these are chemical methods to prepare colloids. Then there is electrical disintegration or Bradig's arc. Okay, this process involves dispersion as well as condensation. So first there is, suppose this is the aggregate. You have to bring it into colloidal size. Okay, like this. So what you'll do, you'll pass electric current. You will disintegrate. You will turn it into kind of vapor. And suddenly you cool it and they turn colloidal. Okay. Going on further, like soles of metal such as gold, silver, and platinum are prepared. An electric arc is struck between electrodes immersed in the dispersion medium. Intense heat vaporizes the electrode metal and which condenses in the cool water to form particles of colloidal size. So these are electrodes. Particles will intense heat. Here there is heat. So particles will get vapor. Okay. They will vaporize. See, they will vaporize. But suddenly when they come in the water, it is cold. So they will become colloidal particles. Just that much. Then peptidization. It is converting a precipitate into sol by shaking it with dispersion medium, presence of electrolyte. So what happens is there is a, so this is the dispersed phase. You have to mix it in the medium. So you add an electrolyte, okay, it goes, gives this a charge which is attracted by the dispersion medium and it suddenly converts into a colloid. So on adding electrolyte, it gets converted into colloid. This is called peptidization. The agent added is the peptizing agent. It is used for freshly prepared precipitate. It is used to convert it into a colloid. During peptidization, the precipitate absorbs one of the ions of the electrolyte on its surface. This causes development of positive or negative charge on the precipitate and they break up into smaller particles of size. So what happens? Preferential adsorption is there. So if these are the molecules which are held together, now you add some ions. So all of these molecules absorb a negatively charged ion preferentially on them. So they will all repel each other, right? And they will again form a colloidal solution. Purification of colloidal solution. So we are done with the preparation. How to purify? Simple answer is dialysis. How do you dialyze? This process is used for reducing the amount of impurities to a requisite minimum amount. Okay. First is dialysis. Diffusion is used. Membrane is used. So you put the Sole in a bag with the impurity, and you dialyze, allow it to diffuse in water. See, water which is free from electrolyte. So all the electrolytes in the dialyzing this bag, which has the sole also, will diffuse into the water because water has low concentration. Whereas the sole particles cannot diffuse out because they are big, right? Sole particles, colloid particles are bigger than the small electrolyte, small ions. So these ions will diffuse out in the water, and you can just keep removing water and you can purify the sole to a maximum degree. Next is your electrodialysis. Nothing here, just apply electric field. This will also attract the electrolytes even more. So this is a bit faster, right? It is made faster than the normal dialysis. Then there is ultrafiltration. Here you have a specially prepared filter called the ultrafilter, which is permeable to all substances except the colloidal particles. Now, how do you prepare it? See, you take a normal filter paper. How do you reduce their pores? You impregnate it with colloidal. It will make it thick and stop the flow. Like it will make it thick and reduce the size of the pore. And this colloidal solution is a 4% solution of nitrocellulose mixed with alcohol and ether. Right? You soak it in colloidal solution, harden it using formaldehyde, and then dry it. So you have your ultrafilter ready. Ultrafilter paper, use it to separate the dispersed phase from the dispersion medium. Yeah, it can separate the particles in a colloid. It has that capability. Usually they cannot be separated, but this is so thin that the pores are so thin that they can separate the particles. Okay, then we have properties of colloidal solutions. So can you imagine what kind of properties they might be having? See, in the beginning I told you they are something in between of solution, true solution, and suspension. So the properties also resemble this nature of the colloids. They are somewhat in between of true solution and suspension. What does that mean? That means that they might, they don't show all the properties of true solution. They don't show all the properties of suspension. Some properties of both they kind of show. But there are some characteristic properties of colloids which defines them as colloids, which gives them their uniqueness in being a different kind of mixture. Different kind of mixture as in different from true solution and suspension both. First off, this is the colligative property. So colloid particles are actually bigger, right, as compared to the particles in a true solution. So the values of colligative properties are of smaller order as compared to the values shown by true solution at same concentration. See, concentration means amount of substance. So suppose in a true solution, this is going to be the pattern of substance present in the beaker. But in a colloid, it will be something like right. It is going to be something like this. So colligative properties, here you have 9. Here you also have 9, but the number of particles which are behaving as particles are only 3. So yeah, this will give higher colligative properties. This will give lower order colligative properties. Understood? It cannot be true solution in this sense. Colligative properties, true solutions will be having more. Something called the Tyndall effect. What is the Tyndall effect? The homogeneous solution placed in a dark is observed in the direction of light. It appears clear. If it is observed from a direction at right angles from the direction of light, it appears perfectly dark. So what do they say? They say ki, suppose this is a beaker filled with a homogeneous solution, homogeneous like true solution, and you have a light source. You pass the light source. Okay, it comes out like this. If you see it from here, you will see it to be perfectly clear. Okay, because none of the particles in the solution will reflect or refract or distort the ray of light. And if you see it from the side or right angles to the, see, this is the path of light, this is how you're seeing, they are at 90-degree. Understood what right angles to the path of light means? You see it from here, it will appear completely dark because there is no light coming, there is no light which is being reflected. So it is completely dark. So from side, you will just see darkness because light is just going like this. Only if you are seeing from the like behind, you are seeing the behind, from behind, you will see the ray of light. This is what a true solution does. But in a colloid, there are particles. The particles are of bigger order. Okay. So they will scatter the light in various directions. So in front, though it is going to look clear only. But in this from the side, it will not be clear. It will be bright, and you'll be able to see the path of light. What does that mean? I'll draw the same perspective. If this is the face and this is your torch, you will basically see path of light in the solution, not outside the solution, but in the solution, you will see path of light. Why? Because these particles are directly scattering light towards you, particles of the colloid solution, big particles, and you can only find the scattered light from the particles which are in the path of the light. So you can see the path of light easily. This is called Tyndall effect. See, scattered light you can see under microscope. Colloidal solutions viewed under the same way may appear clear or translucent by transmitted light, but they show mild to strong opalescence when viewed at right angles to the passage of light. Okay, observed by Faraday but studied by Tyndall, so known as Tyndall effect. The bright cone of the light is known as Tyndall cone. So this is the Tyndall cone. Tyndall effect is due to the fact that colloidal particles scatter light in all directions in space, illuminates the path of beam in the colloidal dispersion. Right. Two conditions for observing Tyndall effect. Diameter of the dispersed particles is not very small than the wavelength of the light used, and refractive indices are very different of the dispersed phase and dispersed medium. So particle is not very small, and there is huge difference between refractive indices of dispersed phase and dispersed medium, so that distinction could be drawn. Okay, then there are some characteristics. Color of a colloid solution, it depends on the wavelength of light scattered by the dispersed particles. Example, you need to know that mixture of milk and water. Blue when viewed from the reflected by the reflected light, and red when viewed by the transmitted light. So yeah, this is, again, I'll show you one example. See, you view from here, if the light beam is going like this, if you view directly parallel to it, you will see it as blue. Sorry, you will see it as red, transmitted light, because it is being transmitted. If you see it from the side, whatever light is coming reflecting on your eyes by the particles, you will see it as blue. This is what they're trying to say, right? Next is after the color. So this example you should remember. Then the finest gold soul is red in color. As the size of particle increases, it is purple, blue, and then gold. These two examples, please remember it. Then Brownian movement, it is shown by colloidal particles. If you see it under a powerful ultra microscope, there is a zigzag motion, hmm, described by Robert Brown, and it is called the Brownian movement. The motion is independent of the nature of the colloid, but depends on the size of particles and viscosity. Now, the Brownian movement is kind of, it has a stirring effect, which does not permit the particles to settle and as well for the stability of. This is important point about the Brownian movement. Then you have charge on the colloidal particle. There are positively charged soul and negatively charged soul. Positively charged soul is all hydrated metal oxides, basic dye, hemoglobin, and oxides. Then negatively charged souls are all metals, metallic sulfides, acidic dye, like here basic dye, here acidic dye, negatively charged, and souls of starch, gum, clay charcoal, or your macromolecular souls. Okay. There was a kind of mnemonic. Okay, aluminum is there, chromium, iron is there. So all female criminals murder, which stands for hemoglobin. All female criminals murder BAO, BADO, BADO. So BAD stands for basic dye and O stands for oxide. Murder stands for hemoglobin, criminal is chromium ka oxide, hydrated chromium ka oxide, aluminum is aluminium oxide, female is female oxide. And the others, you can remember, whatever does not fall in this criteria comes in the negatively charged soul. Why there is a charge on the soul particles? See, due to electron capture or due to preferential absorption of ions or due to formulation of electrical double layer. What is preferential absorption of ions? What is happening is, suppose you have a potassium iodide solution, you add silver nitrate to it. Okay. The silver iodide will be precipitated and it absorbs the iodide ions from the dispersion medium and negatively charged colloidal soul results. So if there is AB is a compound, it will absorb A minus ions on it, or it will absorb B minus ions from it. Now this A minus ions could be from X plus A ion, B minus ions could be from Y plus some By ion or Xa ion, but it will only absorb its own constituent on its surface. So yeah, silver iodide absorbs iodide, creates a negatively charged colloidal soul. But when Ki is added to AgNO3, Ag plus is absorbed. So yeah, see, if iodide is absorbed, negatively charged. If silver is absorbed, it is positively charged. So AgNO3 is added to Ki. Then iodide is excess. It will be absorbed. But if Ki is added to AgNO3, then Ag is excess. So it will be absorbed. This is how you can remember. Next example, FeCl3 is added to excess of hot water. Excess of hot water. Then positive soul of hydrated ferric oxide is formed due to absorption of ferric ion. But if FeCl3 is added to NaOH, negatively charged soul is formed due to absorption of OH minus. So remember both of these examples. Now this is the soul with its adsorbed ion. Now it will also attract the other ion because the soul is now charged. So it forms kind of, this is the soul. This is the first layer of adsorbed ion, second layer of attracted ion. Attracted and adsorbed. So there are 1 and 2 layers. The second layer is there is a double layer. Okay, double layer, and there's a difference of potential because this is plus, this is minus. So there will be a potential difference. This potential difference is called zeta potential. electrokinetic potential of or zeta potential. Okay, electrophoresis is nothing. You apply you know it is used to check the charge of the you apply a electric field, and they will start the colloid particles will start moving towards the opposite charged electrode. Coagulation or precipitation, either due to gravity, or you can add some other, by electrophoresis, by gravity, by mixing to oppositely charged sole, by boiling. All these are, I'm telling you, the methods of coagulation. See, electrophoresis is nothing. It is like colloidal particles move towards the other charged electrode. So positively charged particle will move towards cathode, negatively charged colloids will move towards anode. Now, coagulation, first was gravity, second was electrophoresis, third was mixing to opposite soles. There is an example. Mixing of hydrated ferric oxide positive sole with arsenious sulfide negative sole brings the precipitation, because charges are lost. And why? If charges are lost, then they will get aggregated, because it is the charge which is repelling them from each other. This has negative charge, so they will get repelled and they will be in continuous motion in the colloid. They will remain stable. But if the charges are lost, they will aggregate. Mixing to oppositely charged soles will aggregate both of them. By persistent dialysis, you do prolonged dialysis, again loss of charge will be there and they will settle down. Or by addition of electrolytes, again you're removing the charge by adding a opposite electrolyte. So there is something called the Hardy-Schultz rule here. So in the coagulation of the negative charge sole, the flocculating power is in the order of this. So if you have to coagulate a negative sole, so you add a positive ion. And if you add equal moles of Al plus 3, barium plus 2, and sodium plus, which will coagulate more, because this can utilize 3 charges, this can utilize 2, this can utilize 1. So aluminium is the most effective here. That is called flocculating power. Similarly, positive sole coagulation, flocculating power of the negative ions will be based on their charges. So yeah, -4, -3, -2, -1. Then one more definition: minimum concentration of electrolyte in millimoles per liter requires to cause precipitation of sole in 2 hours is called coagulating value. The smaller the quantity needed, the higher will be the coagulating power. Don't get confused between coagulating value and coagulating power. Coagulating value is the amount of sole required to precipitate, amount of electrolyte required to precipitate a sole in 2 hours. But if the coagulating value is more, which means the more electrolyte should be added to precipitate the sole. If it is less, then only a less number of electrolytes will do. So which case power is more when the coagulating value is less. Coagulation of lyophilic soles, although really stable, but they can also be coagulated by adding an electrolyte and adding a suitable solvent. Okay. When solvents such as alcohol and acetone are added to hydrophilic soles, dehydration or dispersed phase occurs. So adding a suitable solvent like alcohol or acetone, which is kind of your hydrophobic, to a hydrophilic sole will dehydrate the dispersion phase and it will settle down. Protection of colloid, again, what is protection? How you protect a lyophobic sole? Something you add, which was called the stabilizing agent. Now they have a unique, the lyophilic colloids have a unique property of protecting lyophobic colloids. So protecting soles are, protection of colloids is achieved by adding the lyophilic colloid to a lyophobic colloid. The lyophilic particles form a layer around the lyophobic particles and thus protect the latter from electrolytes. So lyophilic colloids used for this purpose are called protective colloids. I think just a definition. Then we come to emulsions. Emulsions are nothing. There are 2 kinds of emulsions. See, they are just covering the kinds of emulsions: oil in water emulsions and water in oil emulsions. Emulsions of oil in water are unstable. Then see, We'll start from the beginning. There are two kinds of emulsions. One is oil dispersed in water, oil in water type. One is water dispersed in oil, water in oil type. So in oil in water type, water acts as a dispersion medium. Milk and vanishing cream are example. In milk, as I told you, liquid fat is dispersed in water. In the second system, oil acts as dispersion medium, and common examples are butter and cream. Now, emulsion of oil in water are unstable. The first kind, and sometimes they separate into two layers on standing. For stabilization of an emulsion, an emulsifying agent is usually added, forms an interfacial films between suspended particles and the medium and keeps them stable. For oil and water emulsion, the emulsifying agents are protein gums, natural synthetic soap. For water in oil, heavy metal salts of fatty acid, long chain alcohol, black. These are kind of the oil and water. You have macro molecules again, and for this one you have metals and hydrocarbons. Okay, colloids around us. Blue color of the sky is due to scattering of light by the colloidal dust particles. Okay. Fog, mist, and rain. Again, examples of colloid. Food articles like milk, butter, etc. are colloids. Blood is a colloidal solution. So, action of alum and ferric chloride. So they form a coagulation of blood, forming a clot. What happens is blood is stable, liquid medium, colloid. So if you just precipitate it, it will become coagulated. So how do you precipitate it? Add alum. It is a precipitating agent and it creates coagulation of blood. Formation of delta. Okay. Water of river is a colloidal solution of clay. Seawater contains electrolytes. So when river water meets the seawater, electrolytes in seawater coagulate the colloidal solution of clay, and a delta is formed. Application of colloid, electrical precipitation of smoke. This is the diagram. Purification of drinking water, medicines. Okay. Tanning, cleansing action of soap, photographic plates and films, rubber industry, industrial products. Next, we go on to pre-BYQs. First question is, for colloid particles, value of colligative properties are smaller orders than true solution at the same concentration. Statement 2 is, for colloidal particles, potential difference between fixed layer and the diffuse layer of the same charges is called the electrokinetic potential. No, it is of different charges. So statement 1 is true, but statement 2 is false. Next, which of the following would coagulate the colloidal solution formed when FeCl3 is added to NaOH? So FeCl3 is added to NaOH, it forms a negative Sol. We read it just now at the fastest rate. So here the positive ion is Al plus 3. Here it is Na plus. Here it is Ca plus 2. Here it is again Ca plus 2. So which of these? See, they have also given concentration. So let's find out the number of Al plus 3 here. So 10 ml into 0.2 and charge is plus 3. So in the first, it is 2. This is 10 over 2. This is 1. This is 1 into 2. See, there are 2 sodiums. So this is also 2. There are 3 calcium. So 3.5 into 1, 1.5 into, there is only 1 calcium. So 1.5. Multiplied by the charges. 2 into 3, 6. 2 into 1, 2. 3 into 2, 6. And 1.5 into 2, 3. Although there's a clash between these two, but because the charge on aluminum is more, so AlCl3 is the best fastest coagulating agent here. Now, next question. On adding surfactants in non-polar solvent, micelles will look like. How will they look like? This is the polar head. This is the non-polar tail. Of course, the polar head will be facing outside in a polar solvent, but this is a non-polar solvent. In a non-polar solvent, the polar head should be facing away from the solvent, which is inside, and non-polar tails will be facing towards the non-polar solvent. So yeah, we got our answer. It is this. Don't get confused. It is a non-polar solvent. It is not a polar solvent. Otherwise, this would have been the answer. So answer is your A. See, choose the correct option also. Okay, A is given in the third option. Don't just write first option for A. Avoid silly mistakes like this. Let's go to the next paper. For colloidal particles, statement 1 says values of corrugative. Oh, it's just the same. Huh? It's just the okay. They've just given the solution here. This is the second paper. So see, they have given the double decomposition example. See, I told they're giving direct questions. So which one of them is oxidation, reduction, double decomposition, and all? See, hydrolysis is fourth one. Oxidation is your second one. Reduction is third one, and I think the correct option is I think this is the correct option. Next, lyophilic sols are more stable because there is strong electrostatic repulsion between negatively charged colloidal particles. No, colloidal particles have a positive charge. Colloidal particles have no charge. Colloidal particles are solvated. I think the answer should be colloidal particles are solvated because they are solvent loving. Tyndall effect is more effectively shown by, I think, more effectively shown by what? Lyophobic colloid or suspension or lyophilic colloid? See, since it's a colloid question, it should be lyophobic colloid. Then sol given below with negatively charged colloidal particles is FeCl3 added to hot water, it is positive. Ki added to AgNO3 solution, it will again be positive because Ag plus will be adsorbed. AgNO3 added to Ki solution, this is going to be answer. The last question is, so the last one is incorrect statements regarding colloidal solution. First says the colloidal solution shows colligative properties. This is correct. Ordinary filter paper can stop the flow of colloidal particles. This is incorrect. Third is also correct. Al plus 3 flocculating power is more than Na plus. Charge is more. Fourth one is also correct because colloidal solution shows Brownian motion. For the coagulation of a negative sol, highest flocculating power. So it should be a positive ion, and this has the most number of charge. So barium plus 2 will be the answer. Next, charges on CDS sol and TiO2 sol. So TiO2 is a metal. TiO2 is a metal oxide. So it will be negative. CDS. CDS is again a metal. So this will also be negative. So both are negative. So yeah, we are done with all the question answers. So yeah. Oh, I'm really sorry. Here oxides are positive. I just marked oxides as negative. So answer will be fourth. For oxides, should be